So tomorrow night, 6 o'clock or what? 6? What's that? 5 o'clock. Okay, tomorrow 5 o'clock. And where is the place you want to meet them? In your lab? In our lab? Okay. So if you guys have any problem with your final grade of your midterm exam, tomorrow 5 o'clock, okay, and TAs will find a room, discussion room, to discuss with you, okay? Take that, all of them with you. What's that? What's that? Answer sheet? Okay. Could you please bring back your answer sheet and the problem sheet? Tomorrow, 5 o'clock, okay, please give all the answer sheet and problem sheet back. Tomorrow, 5 o'clock, and the OTAs will tell where to meet to discuss your grade. Is that all right? Tomorrow, 5 o'clock. All right, have your seat, please. Let's continue our dynamic logic. So we are going to have a final exam exactly the same as a midterm exam. Open book, okay? You can have everything. All right, please be back 5 before 12. All right, thank you. So let's continue our discussion of the dynamic logic. Oops. So how the hell we can avoid the hazards? Okay. First thing first, I explain what happened. Okay, if one of the MOS in the M block is accidentally turned on, what kind of problem that it will create? Okay, it is called the charge sharing. Remember the possible erroneous state when you cascade two dynamic logic together? That's what happened. Okay, now this is a theory. It's a very simple one. Please pay attention to that. Let's assume we have two capacitors, and at the beginning they are both, they are respectively charged to V1 and V2 on both sides. Okay, so the overall charge, according to the basic circuit theory, we are going to have C1 times V1 plus C2 minus V2. That will become this way. All right, now let's close the switch, okay, so that these two capacitors, they are shorted together, become parallel. So the overall, because they are parallel, and the final voltage after the switch is on, it's become the V. So they are parallel, so the summation will be the overall capacitance with the summation of these two capacitors. So using the basic linear algebra, we can find this answer. Okay, charge sharing. Now, we plug in some numbers because students like numbers. 10, this is 20, and 0 is 1.8. Okay, what's going to happen? Okay, after you close the switch, and the final voltage will become what? 1.2. 1.2 is not 0, it's not 1. It's somewhere in the middle. So if you accidentally turn on one of the transistors in the N block, you might create the same problem over here. Okay? So this is how it works. Okay, this is called the charge sharing. So what are we supposed to do with that? We're going to find some way to get rid of this problem, because this is a problem that we don't like, because that will give us something we don't know. Okay? This is why the erroneous state will happen. So how do we do that? Okay? Now this is the charge sharing problem. Okay, pay attention to this, please. Okay, let's assume we have a C1 load over here. This is a load. Okay, stands for stands for the inverter. And we have 3 inputs. Okay, don't you forget that parasitic capacitors are everywhere. All right, so we have parasitic capacitors in the middle of A and B, and another one here in the B and C and B and the C, and the last one with the C and the foot switch. Okay, now let's assume A, B equal to 1 and C equal to 0. That means these 2 transistors are on. Okay, so if we do the pre-charge, so let's assume C1 initially pre-charged to VDD. So when we are in the phase, pre-charge phase, that is clock is 0, this is off, another one is on. The C1 will be charged to VDD. And C2 and C4 are pre-charged to ground. So all the capacitors are equal to C. Let's assume they are the same size. So the VC1 over there will be what? 3C over C. Then it will become only 1/3 of the VDD. That's tragic. Okay. Now let's increase the size of the load. It becomes 6 times. And then the C2 and the C3 and the C4, they are the same. They are parasitic capacitors. Okay, they are unit. Then the VC1 is elevated a little bit higher to 3/4 of a VDD. So these 2 examples tell you one thing that is very important. What is that? So if the size of the load is the same as the parasitics, then you have a problem. Because of the charge sharing, the final logic value will be pulled down so low that you cannot tell what that is. Okay, you cannot tell. The only solution, okay, by this kind of simple formation is that we have no choice but to increase the size of the load. Okay, this is only a single unit. Right now we increase by 6. Then we are going to have what? 3/4 of VDD. That is close to the logic 1. So let's assume, okay, what's going to happen is, what if we have 10 times? What is 10 times? Okay, the VC1 will become very close to, okay, 10, 11 VDD. I'm not sure whether my calculation is correct or not. 3 C's. Okay, hold on a second. 10 times 10 and 12, sorry. 10 plus 1 plus 1, that's 12. Overall is 10 times. Okay, this is really close. So if you keep increasing the ratio of the load versus the capacitance, that means the load is big. And relative to the to the parasitic capacitors, then you increase by, for example, 50 times. Then you're going to have 52 over 50. This is close to the VDD. So just all you need to avoid the charge sharing is that you have no choice but to increase the size of the load. Is that clear? Okay, so based on the equation and the examples over there, that's how you solve the problem. But the price to pay, that the trade-off is that the speed will be slow. Because right now it's 10 times or 50 times or 6 times, because it will take time to charge the C1, take a long time. Because the charging time equal to what? R and C, the product of R and C. So the charge time will increase linearly. So it's a trade-off between speed and accuracy. Okay, that's a problem of dynamic logic. So I just tell you this example. Okay. Another way to solve the problem is using the keeper design, okay, that we apply in the PTL. So the first one is that we use a single teeny tiny PMOS, which is always on. But this kind of solution, okay, it costs DC power, so it's not welcome. But here, this is another solution. We use a keeper. Okay, when this is 1, right? Even though that it is dropped, it is pulled down a little bit by the one of the NMOS transistors over there. And the 1 over here, and we got a 0 on the output of inverter. Then 0 will turn on this one. Okay, so that all the charge that, that was taken away will be pulled back, compensated by this extra device. This is called a keeper. Okay, the keeper could be a single inverter, or can be done by this way. It's a practical implementation. Okay, this will become the switch, and this is a current source. So this is charge keeper. Okay, and no matter which one you use, they cannot be too large. Basically, this kind of devices, or called the keeper devices, they are very narrow width, but with a long length. Okay, narrow width, because we don't want that this device to fight with the main block. So it got to be a very weak device. Weak device means the length is long. Okay, use a keeper, charge sharing. So you either increase the size or you add extra devices to guarantee the functionality of the dynamic logic. I'm sorry? Okay, so there are several types of a single rail dynamic logic. The most important one is a domino. Okay, domino, there are several types. Basic domino, multiple output domino, MODL, compound domino, okay, or noise tolerant pre-charged logic. So I think we only, because the time is not the luxury we have, we might be able to cover the domino logic, maybe MP domino, MP NORA. But well, listen to what I say here. Domino is the most important one. The rest are just garbage, okay? And dual rail. Dual rail can be evolved from the single rail, okay? And for the clock dynamic logic, okay, we have also have a single rail and a dual rail logic. So let's go to the domino logic. This is perhaps the most important one besides the basic dynamic. Okay, remember what the problem is when we cascaded the two dynamic logic together, right? So there is a hazard that the G over here could be the problem to pull down to turn on a certain N transistor in the N block in the second stage, so that the output over here will not be as high as we expect. It's called the partially discharge hazard. Now, I'm telling you why this happened. Okay, there is a feature in dynamic logic called monotonicity. Mono means that it's either going down this way, decreasing, or going down that way, increasing. So monotonicity is an important feature that dynamic logic has a problem to deal with. Okay, let's look at the simple inverter over there. Okay, I'm going to redraw the simple inverter so that we understand what we're dealing with. Okay, why dynamic logic is so important. Okay. We have a foot, as we expect before, and this is A, and this is Y. Okay, so what happened is that there are 4 scenarios. Okay, if this is an inverter, basically we like the inverter to see this way. We have a 0, we got 1, we got a 1, we have 1 here, we got 0. This is typical definition of an inverter. Okay, if this is dynamic logic, static logic. So what happens is, if this inverter is driven by a clock, it becomes a dynamic logic. Whether this feature can be maintained or kept over there, there could be a problem. Okay, now let's see what happened. Okay, let's look at the clock over here. Oh, this is a clock. Right? This is a clock. Okay, the clock. And then I draw this for you. Okay, so this is the pre-charge. Over here, pre-charge. So the Y should supposed to be 1. The Y is pre-charge. Sorry, up here. Pre-charge is over here. Okay. When this is 0, it's off. It's on. So this is Y over here. So Y will be 1 in the pre-charge phase. Then, when the clock is pulled high, we are going into the evaluation phase. Evaluation phase. So it depends on what A is. If A is high, okay, if A is high, then no problem that this one will be discharged. So there's 2 possibilities. Okay, one is going down, the other one stays the same. Theoretically, no issue. Theoretically, no issue. Okay, so if A is given before this one, A is given before this one. If A before this, the timeline over here is high, then we have no problem. After the evaluation, it will drop to 0. If A is 0, okay, then even though that this one is pulled high into the pre-charge phase, then 0, that will become this way. Okay, no problem at all. Okay, no problem at all. As long as the A is stabilized before the rising edge of the clock, everything's perfect. Now, the only issue is that what happened is that A is changed during the evaluation. A is changed, okay? So what happened here? So this is a timeline. So this is a timeline over here. So there are 2 possibilities, okay? If A is 1 to 0, this is A. After the rising edge, A suddenly is dropped. Suddenly it's dropped. What we expect to have a Y. Oh, I'm sorry. This is the extreme case. I'll tell you this, okay? If A is still the same, no issue, okay? Because if A is all high, then it's ready before this one. So this is high, then it will be pulled down. This is good. Now the second is that A is always 0. Always 0. So the output will be all kept high, no issue, no problem at all. The only thing that we concern is A is changed during the evaluation. So if A is changed, switched from 0 to 1, from 0 to 1, during the evaluation, what's going to happen? Okay, that is, during the evaluation, okay, during the evaluation, before the evaluation, pre-charged, when it is pre-charged, this is equal to 1. And this is off. This is 1. This is on now. So at the beginning it's 0. That's fine because it's a block. 1 stays there. But when A is pull high, then the 1 over here will be discharged because this one is on. So when A change from 0 to 1, the Y will be dropped. 1 to 0. No problem at all. This is good. So during the evaluation, if the input is a pull high, the output will be a pull down. It's perfect. So for these 3 cases, 1, 2, 3, they are all good. Now the only problem left is the last case. What is the last case? The last one. The last one is A initially is 1, but it drops to 0 during the evaluation. According to the definition of inverter, when this is 1, this is 0, we are going to have the reverse, 0 to 1. Okay, but the problem for the Y is that it's impossible to be done. Because this is 1, right? At the beginning, this is good, it's all 0. But the problem right now is we want to put it high. But here, look at this. When the beginning of A is high, then this is 0. 0, right? And this is turned on. Now A drops from high to low. It's discharged. Now A drops to 0. We want logically Y could be pulled high according to the definition of an inverter. But it cannot be done because what? Because during the evaluation phase, this one is denied. There is no way, no current, no voltage can be sent, delivered to Y. So this way, this is a case that it will not succeed. When A drops from 1 to 0, we like to have the dash line over here. According to the logic of an inverter, we like to pull high. But the thing is, during the evaluation, that the PMOS is turned off. There is no current pass to pull high the Y. So logically, this one will be wrong. So this is the problem of dynamic logic. Dynamic logic cannot satisfy the basic rule for all cases. One of these 4 cases will fail. That is, there is no current path to bring back the logic to high during evaluation. That is a problem of dynamic logic. So how do we do that? Because the dynamic gates require monotonically rising inputs during evaluation. It cannot work when the input, from high to low. It's impossible. It cannot be done. So we need to do something about it. It cannot put it high. So how do we do that? There is another bad thing. Because of this feature. So if now we cascaded two inverters, both are driven by the same clock. It's even worse. See that? During the pre-charge, X and Y, they are both high. No problem at all. They are no problem at all. But right now, what's going to happen? during the evaluation phase, okay, phi will be high. So both of these PMOS will be denied, okay? So this is high, and then X will be dropped from 1 to 0. Drop to 1 to 0, then based on the observation in our previous slides, for this case, the input drops from 1 to 0, but so that the Y here cannot be pulled high. It's impossible, because why? Because this one is denied. This one is denied. So if this is what happened, okay, because we have a scenario 1 to 0 of the input, so that it will cause the failure of the second stage. So the Y should rise, but it cannot. So dynamic gates produce monotonically falling outputs during evaluation. It's illegal for one dynamic gate to drive another. So that's why we call this the problem of dynamic logic, because it violates monotonicity. So how do we solve that? This guy is very smart. This guy say, between any two dynamic logic, we need to add a static logic, a static inverter here. This guy is going to help us, because when this is high, right, X will be 0. Because it's not a dynamic driven, it's static logic. So in the pre-charge phase, W will be 1, X will be 0. X will be 0, guaranteed. So when X is 0, then there is no risk for Y, okay, to be pulled down, because this one is blocked. Guaranteed, this one is blocked. So this is 1 pre-charge. In the pre-charge, 1, 0, block this one, so Y will be safe. Y will be safe. See? As long as we have the initial condition of the input to be 0, then it will work. So we use the static logic to guarantee the input of the dynamic logic to be 0. Okay, to be 0. And in this kind of formulation, we combine a dynamic logic with an inverter. We call it domino. Okay, we combine this one with this one. We call this domino. Because all the evaluation, okay, is carried out by this way: W, X, Y, Z. So one event after another, they are carried out in sequence, just like the domino. Okay, so if you see the symbol, this is a NAND gate driven by a clock. NAND gate driven by a clock. And in the middle, we have an inverter. This inverter is used to guarantee there is no problem. Okay, there is no problem to drive the next stage. The same over here. And this is the symbol that we use. Okay, we combine these two together to be an AND gate, So they can be directly cascaded together without any problem. So this is called a domino logic. It's called a domino gate. Follow dynamic stage with inverting static gate. So dynamic and static pair is called a domino gate. This is very, very popular, and it works just fine. It guarantees that the monotonic outputs are generated so that there will be no risk that the function will fail. Okay, the price to pay or the penalty is that we need inverters. We need inverters at the output of each dynamic logic. So this is domino. It's not an advertisement for the pizza, but this one works just fine. Okay, I guarantee that it works because a lot of my previous students, graduate students, have realized this one. So this is the generic format. It's called a dynamic logic. Domino logic. This is N block. No matter N block or P block you use, at the output we add an inverter. At the output we add an inverter. That's it. That's it. So place a static inverter at the output. Can only realize positive functions because it only realizes either the AND function or the OR function. It cannot implement the negative function. It's a good stuff. It works just fine, all right? Well, the rain stops, too bad. We need more rain, otherwise a drought could be a problem. We don't have heavy rain in the last 600 days in Kaohsiung. But it's not fair because northern Taiwan, they have a flood. In Taichung, they have a flood. And I heard from the news that China has a very serious flood in Jiangxi province. Okay, but the Kaohsiung, Tainan, and maybe Pingtung, we are all suffer from the drought problem. It's really not fair. Well, the climate shift is a very dangerous issue to all the human beings. And I don't mean to be environmentalist, but well, I only have like maybe 2 decades, maybe 3 decades in the rest of my life. But for those offspring or our kids to come, we got to give them a better environmental state. Okay, it's kind of sad. It's really kind of sad. Well, it's not in the scope of this course, but I'll tell you one thing. Okay, right now, about 10 years ago, okay, about 10 years, I think about 10 years ago, all the computation that people used using the silicon-based computers or a lot of PDAs or mobile phones, okay, generate about 2% of carbon dioxide of overall the planet. 2%. It's a lot. The computer you use over there, or the cellular phone, okay, everything on silicon generate 2% of carbon dioxide. I think the ratio right now is a little bit higher. Because of what? Because of artificial intelligence. Remember the story I told you that the only problem ahead of artificial intelligence is power, it's energy. Because right now we rely on the intensive computer power to realize the AI. But the thing is, have you ever seen the movie called The Matrix? Matrix, right? Okay. They assume there is a war between the robots and the human being. And the silly human being use a nuclear weapon to create a cloud so that they can block the sunlight. And that's a way to stop those robots to harvest energy from the sun. It's kind of silly. But the thing is true. Why? Because all the computers need power. And particularly for the AI. So if right now, according to based on the current technology, we need more and more power plants, maybe nuclear power plants. Recently, a big guy trying to run the office of a president, he said that he wants to build a power plant in a drawing station over there. Okay, I don't say he is wrong, but it's kind of silly. You know what is silly? Because the power plants needs a lot of water, and it never work. If you put a power plant in a drawing high-speed rail station, it's impossible. You need close to the shoreline, because we need seawater to cool down those stuff. Anyway, I'm telling you that the more power plant we use, okay, the more serious about the carbon dioxide, XO2, CO2 emission, that will bring us a disaster that cannot be restored. That is called the greenhouse effect. Greenhouse effect will cause so-called the permanent climate a shift. Okay, and that is a movie which is called The Day After Tomorrow, Predict in the Future. And it might be true. Yeah, it might be true. You never know what's going to happen, all right? So it's not a lie, it's a fact, and it's happening. But the AI, the only thing that I think that we can stop the development of AI is the power. We call that the power war. I'm not sure whether I told you this story or not. Back to 7 years ago, 2016, there was a chess game between the South Korea player, which was the top chess player in the world back then, 2016. He had a game with AlphaGo. Of course, AlphaGo beat the South Korea chess player, okay? But the thing is, that game, single game, AlphaGo needs $30K US dollars electricity bill, 30,000 US dollars electricity bill. But the chess player only had a lunch, 30 US dollars. It's 1,000 times of a power. Okay? So the power is the final barricade, final problem for the AI development. I don't think we can afford it because we need hundreds of power plants. Besides that, we need a limited number of servers and storage to carry out the AI that we like. And that's a problem, right? But I'm so glad I won't see that one coming because before I die, but you guys might suffer. Too much power plant will create a problem of a serious emission of CO2. That's bad. Anyway, okay, this is the AND gate and OR gate. You realize the domino logic, okay? See, look at that. This is an AND, followed by the inverter. This is OR, followed by an inverter. These are AND and OR gates in domino logic. All right? And because of the inverter, okay, sitting in between of any two any two adjacent blocks, you see that they can directly cascade it together without any functionality problem. So this is how it works. You can use a single clock to drive many domino logic. Just remember to add inverters, add one inverter between any two adjacent dynamic logic, and then it will work. Okay? All right, and another issue for the dynamic domino logic is that because it cannot implement negative function, so it's better for you to convert it, okay, from the NAND NOR into AND and OR. So this is called the bubble pushing. Bubble pushing is quite an easy, quite easy thing. For the static logic, we like to eliminate all the inverters. But in the dynamic logic, it's the other way around. We like to okay, eliminate all the negative logic. So this is quite easy. And this is what, let me put it down here so that you understand what I'm talking about. It is called a bubble pushing. Okay? Let me copy it down. It's quite easy. Oh, this is white over here. All right, we have another one coming over here. Okay? The bubble pushing is called the bubble pushing, or the bubble killing, whatever you want to call it. Bubble. This is bubble. Okay, so how do we do that? Okay, because the dynamic domino logic only support AND and OR, because this is combined is combination of this one and the inverter. Okay, this is NOR plus inverter. So this is the only thing we can do. Okay, dominant logic only support N and OR. So if you like to realize this kind of a circuits using the dominant logic, you got to do the conversion. So this is NAND and an inverter, NOR inverter. So how do we do that? It's quite easy. So we use the De Morgan's law. So this is 1 equal to by the De Morgan's law, the NAND. Okay, we can do that. It's the same. So the De Morgan's law, hold on a second, tells us that it could be this way. De Morgan's law, right? So this is inversion of the inputs become the OR over here. So this is bubble pushing. So this one we can simply replace it. Okay, these two bubbles, we can kill each other. And just kill each other. So this one become this way. And the OR is left over here. Okay? And again, we can apply the same rule over here. So this one is replaced with an OR gate included with two inverted inputs, and we can kill the bubble. It's called the bubble push. So this one's left over here. Over here. So this is called the bubble push or bubble killing. Okay? So let me repeat again. If one is dominant logic, because dominant logic only support N and OR, you need to convert all the NAND and NOR into N and OR before you realize it. Okay? And the way to do that is use the bubble pushing or bubble killing methodology, and which is based on the De Morgan's law. Okay? And this is another interesting implementation. One of my students implemented this one before. It's quite amazing. Remember, the worst part of an adder is that the generation of all the carries. Okay? And this guy is brilliant. Okay? Using a dynamic logic, or dominant logically, this circuit generates all the carries simultaneously at the same time. Okay, it's amazing. So the generation of C1 is a G1 plus P1 G0. I think I told you this one before. And the C2 is G2 plus P2, okay, and times G1 plus P1 G0. And we have similar equation going on, so on and so forth. Okay, so if you forget how to do the generation of carry, let me refresh your memory over here. Okay, carry is the longest delay. Okay, is longest delay of the adder design. So usually we spend a lot of energies and efforts trying to shorten the delay of the carries. So why carry happen? Carry out. Okay, carry out. Why carry out happen? Okay, let me repeat again. A plus B equal to sum, carry and the sum. Carry out and sum. Okay, this is very easy, 3 bits. We have 3 bits addition, okay, CR and sum. And this is one give us a big problem, because if you use a traditional way of adder design. Okay, this is A0, B0, and C in. Okay, and the C1 go over here, and this is sum 0. Right? Again, sum is no issue, but you have a very long delay. C1, C2, C3, C4. Carry out, it will be the longest delay, the worst nightmare for any adder design. So apparently this kind of design is not allowed in our course. This is for the elementary kids. But we like to know whether there is an efficient way to generate all the C's at the same time. Okay? That is a very interesting one. So let me give you some example to explain why the equations is so important. Let's assume we have two numbers. Okay? Let's assume we have two numbers. They are meant to be added together. So there are four scenarios. Two scenarios. Let me put a 0 over here. Okay? So we don't care about the carry at this moment. Okay? Whenever we see, okay, a pair of ones, we guarantee there is a carry, right? Whenever we have one in the addend and another one in the other addend, operand, we guarantee with a KL. We don't care about what it is. I don't care. It's a 0, that's fine. It's a 1, that's fine. We're going to guarantee to generate that one. Is that clear? So when AI and the BI we call the GI equal to AI and the BI. That means when they are both high, we guarantee we'll generate a carry. That's guaranteed. Okay? That's one thing. If one of them is 1, the other one is 0, okay, whatever it gives to me, if this is 1, then we are going to 1, 0, 1, we are going to pass a 1 to the next. Okay? So if they are 1, 0, and the other one is high, the other one is 1, so we guarantee to pass the previous carry to the next. If this is 0, 0 plus 0, 0, we are going to have a 0 to move forward. So we are going to have a pass, propagate, if one of them is 1, exclusive. Is that clear? Okay? So we guarantee that both of them are high, we are going to generate 1. And then, if one of them is high, the other one is 0, we are going to pass the carry. The last one is called the kill. When both of them are 0, all the carry will stop right here. We don't set out any carry. It's called the kill. But the kill is not used in the generation because it's going to kill the carry. So it's called a kill. The kill means when both of them are 0. Okay, both of them are 0. So that means AI plus BI and invert. But however, KI will never be used in the generation of carry, so we don't need it. We don't need it, so just take it away. Okay? Now the interesting part is, okay, so when, what are the conditions for the addition of any pair to pass the carry to the next? Okay, so the carry out Okay, there are two scenarios. Either I generate by myself. I generate the carry by myself. That is GI. Or I can pass. Okay, I can pass. Okay, the previous carry. That's it. That is the solution. The carry that generated in this stage based on two possibilities. Either it is generated by myself here, or I can pass, I can help to pass the previous carry to the next. That is this one. The C1, the first carry, either I generate it by myself, or I can pass the carry from the previous stage. Then I will send it over to the next one. All right? So similarly, for the C2, we can have a C2 over here. All right? I can generate by myself or can pass the previous one. That's it. For the C3, I generate by myself, or I can pass the previous one. And the last one, the C4, I generate by myself, or I pass the previous carry. That's it. So this is how the equation is derived. So it's from the basic observation of the addition. Now, what is this to do with that circuit implementation? Check this out. All right? So you look at the number here, you're going to love it. See? There's a C1 over here. C1, there are two terms in the C1. The first one is G1, generated by myself. Okay? When this is 1, this one will be pulled down to 0, right? Then C1 will become high. Brilliant. Or we can P1 and the G1, these two terms. If both of them are high, here will be discharged. This is 0 and this is 1. So it's become 1. So these two terms, okay, or these two pass stands for these two terms. That will carry out the C1. Now let's check the C2. C2 over here, see that? C2 is composed of G2. That is this term, right? And then I can pass whatever the previous carry out is. So this is a pass, including these two terms. Brilliant. Right? Perfect. Okay, so any of these paths is grounded, C2 will be high. This is so brilliant. Okay, and can keep going all the way up. So for the C3, either G3 is on, or the P3 times all of these terms together. That's this one. Okay, and the last one is G4 over here. And P4 times all these terms together becomes C4. Don't you think this is brilliant? Very smart, and it works just fine. Okay, this is so-called the multiple output domino logic, okay, MODL. Brilliant idea, okay? I like it very much. That will save you a lot of pain, and it's based on the theory that we just disclosed. Okay? Okay, MP domino. This kind of stuff is just for the textbook example, okay? None of my students ever realize these circuits. Okay, these circuits is meant to eliminate all the inverters. Inverters for domino logic. Remember, the inverters are needed to guarantee the monotonicity of the domino logic. Right now, somebody say, hey, why don't we just interleave the P block and N block and P block? So the N PNP. So if you arrange this way, there is no need to add inverters, okay? But personally, I don't appreciate this design because why? Because the P block is a huge monster. Okay, even though that you save some cost, okay, of the inverters, but you're going to pay large area of P blocks as well as their slow speed. So this is something I never appreciate, okay? So you can check it from textbook. Besides that, okay, the clocks used for these stages, interleave stages, they are out of phase. The clock, clock bar, clock bar. All right? So this is called the MP dominant logic. You should know it, but I don't encourage you to realize it. Damn, the sun comes up, the rain stops. That's it? It's a sunny day. So the rain is gone. So we're going to suffer again for the drought problem. That's it? That's it for the rainy season of Kaohsiung? You know, the Kaohsiung or southern part of Taiwan, if we don't have the so-called rainy season in May or April, we have to wait for the typhoon to hit us in the summertime, from July to September. And last year, we got 0 typhoons. Nothing. 0 typhoons. That's why we have a problem of drought. Okay, all the water reserves run out of water. All right? And this is another way to deal with the so-called racing problem. We got to use a two-phase clock, okay, two-phase non-overlapping clock. Okay, watch this out. These two clocks, they are particularly specially designed. They are not out of phase. I'm going to explain what is that, okay? So this is a clock 1, and this is clock 2. And check this out. They have the same period, but, okay, different duty cycle. They are not 50-50 duty cycle, okay? They are not 50-50. So the duty cycle of these two clocks, they are not 50-50. Duty cycle stands for the high time. This is a period. Okay, and this is the high time. This is the high. Okay, then duty cycle is the high time over period. Okay, in your homeworks, you are always asked to do the 50% duty cycle, right? That's a normal clock. But however, in this kind of application, we don't use a normal clock. If we do use a 50% duty cycle, we have a problem. What is that? Because the clock is not perfect. So if you use a 50% duty cycle, then this edge, the falling edge here, will be overlapped, okay, accidentally with the second clock, the rising edge of this one. That means these two pass transistors, they could be turned on simultaneously. If they are actually turned on simultaneously, then that means the output of the first stage will be coupled to the next stage. That is a problem of the dominant logic. Okay, dominant logic cannot, sorry, that is a problem of dynamic logic. They cannot be directly coupled together unless you have inverter in between so that it becomes dominant. So you have to ensure that at any given time, one of the two transmission gate is on. The other one must be off. So there is no choice. We got sacrifice the speed. There must be some time in between. We call it dead time. This is called a dead time. That means that we got to have some period of time to ensure both of them are off. Okay, both of them are off. Okay, and how to generate this clock? If you are going to have it is called a non-overlapping. This is a very important concept. Please remember this one. Okay, and then, okay. We call this dead time. Dead time for non-overlapping, this is called a non-overlapping clock. Non-overlapping. If you want to drive the circuit over there, you got to use a non-overlapping clock, and the dead time cannot be 0. Okay, that means the duty cycle there must be less than 50%. Okay, must be less than, both of them must be less than 50%. So it's called a non-overlapping clock. And this, the realization of this a clock generation, you cannot do this. The clock comes in, okay, and then you go to the inverter. There's a phi, there's a phi 1, there's a phi 2. Okay, if you do this way, I guarantee it won't work. It's impossible because there is a delay. There's a delay here. There's a short delay. There's a long delay. And they're not matched. They're not matched. So if you simply use a clock, single clock, and driven by, and then drive one buffer, the other one is an inverter, trying to generate 2 non-overlapping clocks, I guarantee they will fail. It's impossible. Okay, I have some special circuit for you, and it is widely used. Okay, so this is a requirement. It's very pretty picture over here. So the clock comes in, generate a phi 1 and a phi 2. It doesn't work. Okay, and the other solution is that we add a dummy switch over here so that we can balance the delay of phi 1 and phi 2. Again, it does not work at all. Okay, because of the PVT variation, you cannot guarantee the delay of phi 1 will be the same as phi 2. That's impossible. Okay, so this is what we are afraid of. You have something that you don't have the long enough dead time. Okay, so there is a risk that phi 1 and phi 2 might be turned on simultaneously. Same over here. Same over here. So what do we do that? Okay, these are 2 simple strategies, and they won't work. And this is the one that will work just fine. Please copy this down. This will help you a lot if you want to generate a clock, internal clock. How to use that? Brilliant. Clock comes in. This is what? This is a flip-flop. Okay, NOR base, cross-couple flip-flop. So if you go back and check your freshman textbook in the area of digital design, you know that this is a SR latch, and the inverter comes over here. And you can add long enough even stage of inverters. Okay, they are identical. So the longer the stages, the longer the time in between. I guarantee this will work because many of us students use this way to generate the delay, and as well as a non-overlapping clock. All right, it is a little bit complicated, but it is safe. it guarantees will work. Okay, if the dead time is not long enough, you just increase the number of stages over here. That's it. Make it as long as you like, as long as it fits the the requirement. Okay, and I think this is the last one. This is clock delay, the dominant logic. Well, since we are going to have a dynamic output, for example, over there, all right, and we like to generate a delayed clock. The sum of the operations might be delayed over here. There are several ways to do that. 1, 2, 3. 3 ways to generate a clock. The first one is, look at that, this is what we want. Output over there, we like to have a delayed clock. And the more clock you use, okay, I told you before, I was afraid of too many clocks because you have a synchronization problem. So there are 3 ways to do that. The first one is I use a control logic. This is an inverter. Okay, when it is on, then you have inverter after inverter. So the clock is delayed by 2 inverters to become the clock D. That's methodology number 1. The second one is that if this is not good enough, you can do this way. This is a resistor. This is a transmission gate over here. So this is on, this is off. Then you can create a delay over here. Okay, this is number 2. Use the RC delay. And the last one is personal, my favor. What is my favor? Okay, this is a simple delay over here. It's if the dead time or if the delay is not long enough, you add a R and C. This is capacitor. So this is a R. If this is on, then you have RC over there. So it simply changes the size of the capacitor. You can tune the delay. So there are 3 ways that you can generate the delayed clock. Okay, 1, 2, 3. A lot of students adopted the second way. Okay, use a transmission, and that's fine. Okay, and this one it's more brilliant because you can change the size of capacitor to generate the delay you like. So we are going to take a recession here, and as usual, we are going to ask you to give us a report of your excuse me, of your final chip projects. So this is a teamwork that if you want to stay with me for the rest of your study over here. So in the coming week, let me repeat again. You cannot finish your chip design project in 1 week. That's impossible. It's better for you to, do it, gradually, step by step. Okay, distribute all the efforts over the weeks that left in this semester. I'm sorry, that's May 15th. It's not May 8th. I'm sorry, my bad. So in the next week, you will just keep doing the schematic design. However, this week, I ask you to send a report to tell us that you already finished certain blocks of your final chip projects. Certain blocks, that's fine. In the coming week, you need at least 1 level up to integrate, okay, as many blocks as possible in the schematic design and run simulations in these corners. 5 models, 3 temperatures, and 4 VDD conditions, all right? So this is I'm sorry, that's May 15th, my bad, all right, the next week. So in the coming week, you are going to keep doing your schematic design and run a simulation. But the difference between this week and the next week is that you got to integrate more blocks and run the simulations, and tells us that you have done that part. That's all. Okay, that's done. Okay, thank you for coming, and we'll continue our discussion next week.